Hello, my name is Pranshu, and today I'm going to present on a topic quantum computers and Turing machine. Before I start, a little background about myself. In 2020, I started exploring different technologies. That's when I first stumbled upon the term quantum computing and Turing machines, and I also conducted a couple of webinars on the same in my school. So, without further ado, let's get started. So just the content of what we're going to cover today. First, we'll talk about quantum computers, in which we'll cover qubits, classical bits and qubits, Schrodinger's cat, superposition entanglement, and Church-Turing thesis. Next, we'll move on to Turing machine, where we'll talk about Alan Turing, the Imitation Game, Turing Test, and finally the concept of Turing Complete. So, what is quantum computers? So, it is basically a combination of physics and computer science, and using these ideas, we are able to achieve high computational powers. So, let's go ahead and learn with a recent example from Google. So, recently in 2019, Google announced that in collaboration with NASA, they had developed a quantum computer and they had achieved quantum supremacy, which means for a hypothetical problem, their quantum computer was able to solve it in 200 seconds, which on the other hand took 10,000 years for the world's fastest supercomputer. So they were able to scale down the time from 10,000 to 200 seconds with the help of quantum computers. So you can understand the power the quantum computer have over classical computers. So, what exactly is a quantum computer? It is basically the phenomena of combining physics and computer science and exploiting the both particle and wave nature of nature. That is, we are able to synthesize both particle and wave nature into the qubits and exploit both at the same time, giving us these high computational powers. The difference between a classical computer, which is the computer I and you all use right now, versus a quantum computer is classical computers operate on bits, whereas quantum computers operate on qubits or quantum bits. A classical of bits, as you know, takes the values of either 0 or 1. Qubit, on the other hand, takes the value of 0 or 1 or both at the same time. That is, it can be multiple states at the same time itself. This might sound a little confusing, so let's understand it with the help of a familiar concept called Schrodinger's cat. So early in the 1900s, Schrodinger approached a concept where if we place a cat inside a box along with a bottle of poison and close the box, then the cat is basically in two states, both alive and dead. That is, the cat might have opened the bottle and ate the poison and might have been dead, or it did not open the bottle and is still alive. So unless we open the box, we can know for sure whether the cat is alive or dead. That is, the cat is existing in two states at the same time. This might sound a bit confusing that this is the basic notion behind quantum computers and qubits that has been encoded into this hardware, which has allowed us to achieve exceptionally high computational powers. So let's look at a bit more mathematical terms of how we express this idea of quantum computers and how much power do they have over the classical computers. So let's say that you have n bits. So the power number of states that you can handle with a classical bit is given by the formula 2 into n, where n is the number of bits you have. For instance, if you have 2 bits, you have 4 states. If you have 3 bits, you have 6 states. If you have 4 bits, you have 8 states. On the other hand, qubits have exponential power. That is, the formula is 2 to the power of n. For instance, if you have 2 qubits, you will have 4 states. If you have 3 qubits, you will have 8 states. And let's say if you have 100 qubits, you will have such a big number of states that you can handle at the same time. So as you can see, the power, the difference to linear power versus exponential power. That's the basic idea and computational power that quantum computers provide. Another popular concept behind the quantum computers is quantum superposition and quantum entanglement. So it is basically based on the idea of, let's say there are two Schrodinger cats, this time instead of one, and both the cats are in superposition. That is, there is no relation between the cats. So there are a total of four possible outcomes that we can get. First one is both cats are alive. Second is both cats are dead. Third outcome is first is alive, second is dead. And fourth outcome is first is dead and second is alive. Since there is no interrelation between the two boxes, the outcome of first box does not depend on the outcome of second box. So there are a total of four outcomes with a probability of 25% each. On the other hand, under quantum entanglement, the two boxes are interrelated, and even if the space between them is that of a complete universe. They are still entangled to each other, and the outcome of one box is directly dependent on the outcome of another box. For instance, if the cat is found to be alive in the first box, then it must be dead in the second box, and vice versa. So, since there are only two possible states, there is a 50% chance for each one of them. So, let's look at a much more real world example. Let's say, like solving a maze, so you can better visualize the power that quantum computers give. So as you can see this in this video, we are solving a maze, but on the left, as this classical bits are doing, it is randomly choosing one path at a time and traversing it to the end until it reaches the solution. On the other hand, qubits or quantum bits split into two or multiple balls at each and every transition that it has to make a choice on, and explores all the states at the same time. Remember, because as we talked earlier, it has exponential power, it can handle multiple states. Thus, it is able to explore multiple paths at the same time without much computational power. And as you can see, the quantum computer is able to find a solution in much less time. Looking at a real world more examples like forecasting weather, as we all know, forecasting weather takes a lot of time. Usually, the weather itself changes before the classical computers are able to figure out the weather of the future. So, if we are able to develop quantum computers, then we can attach them with the satellites and deploy them in space, from where we will be able to predict the weather much more quickly because of the computation power that the quantum computers have. Another major application of quantum computers might be cybersecurity, where we can have better hashing and password securing systems through quantum computers, which might take thousands or maybe lakhs of years for classical computers to decode. Finally, we'll talk about the concept of Church-Turing Thesis. It is the concept where that any problem that can be solved by quantum computer can also be solved by a classical computer, at least in principle, given that there is no time constraint, that the classical computer is given enough time. For instance, in that Google example that I shared about earlier, the classical computer was also able to solve the problem. The thing was, it just took more time than the quantum computer. Now let's jump upon to the next topic, which is Turing machines. So Turing machine is the idea based on which all the modern day computers are designed these days, and Alan Turing is the highly credited person behind the creation of these technologies. So let's learn a bit about him and his background. So Alan Turing was an English mathematician, and he's primarily known for his work in World War II when he created a machine Enigma that was able to crack the German Nazis' code and help them win war against Germany, which not only saved so many lives but also opened the world of computers and the idea of can machines thing. Later on, after winning the war, he also published a research paper called The Imitation Game, which is very popular and has sparked a lot of debates about the importance of computers and artificial intelligence. So, he published the Imitation Game paper in 1950, in which he proposed the question of can machines think? Can we design machines in such a way so that their own knowledge, they can think on their own and advance that? This eventually led to the development in the field of artificial intelligence and other things. Also, there's a documentary on the same called with the name of again Imitation Game that expresses the entire story of how he cracked the Enigma and how he later on went to write the Imitation Game research paper. In this paper, he also talks about a test called Turing Test, where we are able to set a parameter where we can define whether a machine is intelligent or not. So this steps involves two human beings and one machine. All three of them are locked in separate rooms, where the only way of communication between them is through a laptop. One person is assigned the task of the interviewer, and another is assigned the task of the interviewee. The interviewer randomly takes one at a time and interviews them for as long as he wants, and then he interviews the second person. After that, he is done interviewing. He has to tell which one of them is the machine and which one of them is the human. If the interviewer is not able to determine the correct answer, then we can say that the machine has passed the test. Although this might not be the best or complete test of why the machine is intelligent, it gives us some idea of how machines can be evaluated based on these parameters. So let's understand the actual working behind Turing machines. So a Turing machine basically consists of an infinitely long tapes consisting of squares with values of zeros and one, and there are a set of instructions given to the computer to be performed at each and every state. Each square in the tape represents a certain state at which the computer can be. As you can see in the image, the computer at a particular moment is only able to do one state at a time and just checks the conditions. If it is like, for instance, in the image you can see, if 0, then erase and write 1. So it performs that operations and moves on to the next state as given by the instructions. Another example would be like searching for a name in a long list of long book. For it might take a lot of time for a classical computer to search for a name, but a Turing machine can do it much more quickly with the help of this logic. Let's see how. So as I discussed, there are four key components inside a Turing machine: a tape, an infinite long tape containing different states of values zeros and one, the state which is like the value of the current state the operator is at, the head which is the main eye that we saw in the previous image that is to read and write the tapes and store the previous data, and finally the finite table which contains the instructions to be performed at different states. Let's look at the working of quantum computing. So it is the general example of how CPUs work. It goes to a state, reads the data, reads the instructions, performs the operation accordingly, and the instructions specify which state to go next. So it is this constant step-by-step method which eventually leads to Turing machine to calculating and evaluating the final result. And the data is stored in sequential memory. And this process keeps going on until the head or the operator has reached either a halt state or it has reached the final state behind all this. Finally, we learn about the concept of Turing Complete. So, what is Turing Complete concept? It's the idea that anything that can be done by a Turing machine, any machine that can do what a Turing machine can do, is classified as quantum Turing Complete. For instance, all modern programming languages as C, C++, Java, Python, they can do everything what a Turing machine can do. Thus, they are also called as Turing Complete. So thank you so much for watching. This was all I had, and that's it about me. Uh, this was Pranshu 21BCE1702, and the topic was quantum computer and Turing machine. Thank you.